everyone. Today we're going to start a lesson on the first law of thermodynamics. And if you remember in the last lesson, we defined what thermodynamics was. We defined it as learning about the energy that is in chemical bonds that can be released or gained based on if they're broken or formed. We talked about this being observed as an energy change whenever we see work being done or heat being transferred. So when analyzing these energy changes, we're only going to focus on a very, very small part of the universe, which is extremely large. And we do this in order to keep track of how energy is being transferred, or being absorbed, or being released. There are two definitions that we need to understand going forward, and that is systems versus surroundings. Whenever I use the word system, this is the portion of the universe that we are actually studying, while the surroundings is everything outside of that system. These are bolded and underlined because I would add these to your notes. An example of a system would be if we were studying a chemical reaction, it would be the reactants and the products that are part of that chemical reaction. Everything outside of that, such as the container that holds those chemicals, the temperature in the room, those are all considered surroundings. There are different types of systems. They can be classified as open, closed, or isolated. An open system, matter and energy can both be exchanged. A good example is if you are boiling a pot of water and you leave it uncovered. Energy is entering that system from the heat from the stovetop, and it's actually also leaving whenever that water turns to steam. It's taken up with the water particles that are now a gas. That takes into account the matter. Water is matter, and it leaves when it turns into steam. A closed system are systems that can exchange energy but not matter with their surroundings. So if I put a lid on that saucepan that does not allow gases out, that would be an example of a closed system. The steam cannot leave the saucepan. However, energy in the form of heat can actually still be added from the stovetop. Closed systems can be dangerous if you put a lid on something and too much steam builds up or gas. That's when you can have things explode or shatter. An isolated system is where neither energy nor matter can be exchanged. These systems are kind of very hard to get, and the best example is an insulated thermos, and these are not perfect isolated systems. The thermos actually keeps the matter inside of it. Coffee cannot enter or leave it, and neither can energy. The coffee stays warm because energy's not leaving or heat's not leaving that system. However, we do know that over time it will cool down. So like I said, it's not a perfect isolated system, but it's our best example. Going into what we've been talking about, thermodynamics, there are three laws, and we're going to talk about the first one today. It's not bolded or underlined, but I'm going to star it because you need to understand this. It's going to be on your test. The first law of thermodynamics states energy can neither be created nor destroyed. Only, so this word should say only, transferred or transformed. So what I mean by that is transferred, it can go from the system to the surroundings or the surroundings to the system, or it can be transformed. You might have electrical energy can be transformed into potential energy. Since matter cannot be destroyed, any energy that is lost has to be going somewhere. So typically it's gained by the surroundings. That means our overall universe is unchanged. Energy is conserved. That is why the first law of thermodynamics is also called the law of conservation of energy. With our energy, we're going to talk about something called internal energy, which is denoted by the letter E. This is the sum of all the kinetic and potential energies within the system. However, E, while it is important, we are actually focused on the change in E, which is symbolized by this Greek letter delta. So the triangle means that there is a change. What I mean change is the subtraction. our initial energy minus our final energy. A change in E has three parts. The first part is it has to have a number. So if I look up here, 84 would be my number. The second part is a unit. So our units we learned in the last lesson were joules, kilojoules, calories, or kilocalories. Up here, my unit is joules. And the next one is it has to have a sign that tells us which way that energy is flowing. So over here, this one has a negative sign. I'm going to give you a little forefront into what we're going to be learning, but a negative sign means that our system has actually lost energy. Energy flows from the system into the surroundings. With our change in energy, we have to relate this to heat and work because that's the way we exchange it. It gets thrown into an equation. That equation is the change in energy, which is delta E, is the sum of heat. Heat is actually denoted by the letter Q, plus work, and work is denoted by the letter W. And this happens whenever there are any chemical or physical changes. There's some transfer of energy. With that being said, Q and W, they can have positive or negative values depending on what is being done. A Q can have a positive value whenever the system gains heat or if heat goes into the system. It can get a negative value if the system loses heat. W can have a positive and negative value as well. Whenever work is being done on the system, we tend to get a positive work value. When work is being done by the system, or basically on the surroundings, this means I'm going to get a negative value. Both of these values are going to affect my delta E. If I get an overall delta E of positive, it means that my system gained energy. And if I get a negative value for my delta E, that means my system has lost energy. So over here, I kind of summarized it in my sentence form. Whenever heat is added to the system or work is done on the system, my internal energy increases typically. Whenever heat is removed from the system or work is done being by the system or on the surroundings, my internal energy tends to decrease. With that being said, this tells us the direction of heat flow. And when we describe the direction, this is always given in terms of how we view the system. So if we have a positive delta E, that means the system has gained energy, or in other words, energy flows into the system. We classify these as endothermic reactions. Endo meaning entering or into the system. A negative delta E tells me that my system has lost energy to its surroundings or energy exits or leaves. This is classified as an exothermic reaction. EX means an exit. Now remember, we are giving this point given from this point of view of the system, but if our system loses energy, that means our surroundings going to gain it. If our system increases its energy, that means our surrounding has lost it. So here I have a few practice problems. Remember, our equation is delta E equals Q, which is my heat, plus my work. One thing to know, it doesn't matter what my units are in as long as the units are the same. So I'm going to put a little markup here. Make sure units are the same. I have two numbers in my example problem, 1,150 joules and 480 joules. My units are the same, great. But now I have to focus on, will these numbers get a positive or a negative sign? We know that my delta E is going to equal some number plus another number. So here I have heat. It's telling me that my system's losing heat. So that means that number is going to get a negative value. The second number says 480, and this says my surroundings does 480 joules of work on the system. And if I go back, work done on the system tells me my sign is going to be positive. So I can actually give that a positive 480. You can go ahead and add that, and that tells me that my delta E is negative 670 joules. When classifying this, we also need to look at our sign. My sign is negative. That negative tells me that my reaction is exothermic. So remember, a negative value, exothermic. If I were to ask you to classify this, you would call it an exothermic reaction. Down here in the second example, first let's check to make sure my units are the same. They are, we're good. First, then I have to see what's going to happen next. So here it says the system absorbs heat. If you go back, if the system absorbs or gains heat, I get a positive sign. So here I'm going to get a positive 140 plus, let's see what happens with the 85. It says that it does work on the surroundings. So if I go back, if work is being done by the system here on the surroundings, I'm going to get a negative sign. So I'm going to have a negative 85 joules here. When you add those two together, you get about 55 joules of energy. Notice here my sign is positive. Now that my sign is positive, this means I have an endothermic reaction because positive value are classified as endo. Energy is entering the system. I have two other practice problems I want you guys to work with. These are going to be completion, so just attempt them and we'll go over the answers in class. The last thing that we have to cover is state functions. I'm going to define state functions, but the part that I want you to actually write down is the one that I have starred. A state function is just a property that you can give a system that determines its conditions or state. So if I was going to have something, how would I describe its temperature, pressure, and so forth? Now, while that's an awesome definition, the part that I'm focused on is that starred part. The value of a state function, or other words known as the number, depends only on our present state of the system and not the path that the system took to reach that state. E, which stands for energy, that we've been learning about, is a state function. While work and heat, these are not state functions. Here's a good example that your book gives. This is what we're trying to accomplish. If I say we have 50 grams at 25 degrees Celsius and it's liquid water, this is our present state of our system. And our temperature is 25 degrees Celsius. Well, our temperature is 25. We don't care how we got to that temperature as long as we got to that temperature. So we could actually take this ice, add heat to it to get to 25, or we could take the steam and let it cool off and get to 25. The path that it got there, we don't care. It still got to 25. So temperature is another thing that is a state function. The reason that heat is not a state function is because the path matters. If heat went into versus out of the system will actually affect whether it will get to 25.